Now for homework of section 6.2, please do on page 652 problems number 68, 69, 71, 73, 75, 79, 83, 85, 95, 101, 107, 111. And the last problem, 111, the answer is wrong in the answer key, and I will provide the right answer in the video. And so please go do your homework, and then when you're done, come back and we will talk about the homework. Now that you're done with the homework, let's look at some of the problems. First, number 68. It says that we have a base, which is a circle with radius a, and then and there are squares sitting on top of it. That those are your slices. So to see that in 3 dimensions, we only need to see one slice. Okay, so I will draw the circle. This is looking at the circle sideways. Okay, and then we'll draw. So if we look at the circle sideways, then there's a bunch of squares going across it. So we'll draw the squares like this, one square. I'm just drawing one of them. Okay, one of the squares look like that. And then you continue to draw the squares. So you notice that the squares get smaller and smaller when you get to the end, and get fatter until it's equal to 2 radius a. So at the middle is the biggest square, which it becomes 2a. So the squares become small at the end, and then eventually becomes 2a in this length at the biggest point, and then go back to small again. Okay, that's but what this thing look like exactly is not important to our problem. And so now that we realize that, then let's do the calculations. So what is the side of this thing at any given time? Let's look at the circle from top down. Okay, so here's the circle. When we look it down from the top, where then it looks like a perfect circle. And then we have f of x. The equation of a circle is square root of a squared minus x squared. That's something from pre-calculus, I guess, or something. Anyway, if you don't remember this equation of the squared, just look it up. But anyway, it's this, okay, guaranteed, if the radius is a. And then anyway, so once you figure out the equation, what is that? That's this height, okay? That is the half of the length of your square, okay? At any given depending on x. See, when at x the square is actually this thing, but except twice that much. It goes all the way down here. So the entire length of the square is equal to 2 times a squared minus x squared. But we need the area of the square, and then the area, of course, is this thing squared. That's the area of one example of one of these squares, and it depends on x. Okay, as x goes this way, it gets bigger, or goes this way, it gets smaller. Now, eventually, of course, then once the area, you multiply by dx, which is the delta. Represents the delta x, the tiny thickness of your slice, right? And then that would be one of your squares. And then when you sum it up, then it becomes the entire thing. And we're going to sum it up. Now, pay attention to how we're going to sum it up. Okay, we're going to sum it up. Well, being that the squares are identical, we will simply sum it up from 0 to a. And then from 0 to a, and then multiply by 2, because the left side and the right side are the same. So we'll sum it up from 0 to a, okay, and then multiply by 2, and that should give us the whole thing. Now, did I get it right? Right, I think so. Now, at this point, then we are near the answer. So this is an even problem, so we don't have the answer at the back of the book. So I will show you what I did, the details of the evaluation of the integration, and hopefully I didn't mess up. I think I double checked it and it looked okay to me. Okay, so but if I do mess up, then the right answer should also be fairly straightforward, because this, once you square it, this is just a regular power rule integration. And that marks the end of the problem 68. So let's go move on to problem 69. Yeah, that's the next one. Next, let's look at problem 69, where it says that you have a base that's a triangle. That is the standard one, okay, where it goes from 0 to 1 to 1, and then you have a bunch of semicircles that's sitting perpendicular to the x-axis. So this is the top view, and here's your semicircle, and you imagine them rising up like that. So to draw it in 3D, you might be able to see it as well, here's a triangle. Okay, this is three-dimensional, and that's the x-axis, that's the y-axis, and then your semicircles are perpendicular to the x-axis, so they look something like that. All right, now so we are going to calculate what is that. To calculate so first we need to find the area, and the area is this value. Then you need to figure out some of the details. Okay, now what is this line? This line, it goes through 2 points. This is 1 0 and this is 0 1, and so you use the point slope formula, and that will give you the the equation of this line, which is y equal to 1 minus x. And once you once you know the equation of this line, then next we are going to do what is this height here? This height here is equal to, at any given point, if this is x, then the height is also equal to 1 minus x. This thing right here, okay? Because y equals 1 minus x. So at any given point, this thing has 1 minus x, and that is the 1 minus x is the width of your semicircle. And then so the area of the semicircle at this point, let's write down the area. Come on, area. At the area of your semicircle, which I will write it like that, okay, then equal to pi r squared divided by 2, and where r equals to 1 minus x divided by 2, because it's only half a circle. And this is not r, this is diameter, so this also needs to divide by 2, okay, and the squared goes over to the 2 also. And then so by then you realize that the volume then you're integrating from 0 to x goes from 0 to 1. Okay, we're integrating the slices, the thickness of the slice is dx. It goes this direction. Therefore, we're integrating from this area, okay, which is pi over 2 times 1 minus x over 2 squared, which will become a polynomial, okay, of the second degree. And then so the integration will be fairly straightforward. And then we have, and then the slices are going along this way, so it's dx. It's very important to pay attention to whether it's dy or dx, because there was once I messed up and then I couldn't get the right answer and couldn't figure out why. But anyway, the dx, as you can see, is going this direction, okay? And so then this is your tiny little thickness, so that will be so the dx going this way, so then you have to pay attention to that. And where x goes, we're integrating with respect to x, and where x goes from 0 to 1. Having said that, then at this point, then we will clean it up and come up with some kind of an answer, which I got pi equals to pi over 24, which turns out to be the right answer along same as the back of the book. So I'll show you the rest of my steps there, and then you can consult it. But that is how we're going to do problem 69. Next, let's look at 71. So problem 71, we have a region which is so here's a region of problem 71 where we have the upside down parabola where y equal to 1 minus x squared, and then we have a bunch of square slices that's sitting clear across perpendicular to the y-axis. So as you can imagine, the squares will get smaller and smaller when it gets up here, because this is the entire width of the square, and then down here it will get wider. So then so what we do is then we can calculate each square. And we don't have to really visualize the square as long as you remember this is the width of the square, okay, which is the same as the length, being that it is a square. So how wide is that? To calculate that, then we need to express x in terms of y. The y equal to, because the increments, the slices are going up and down this way, so we're going to do dy, okay? And so to do dy, then we need everything in terms of y. So then y equals to 1 minus x squared, and we're going to plug x out of y. So y, we'll put x on this side, so that is positive. X, no, what am I talking about? No. Okay, we need to plug x out. Yeah, let's put x on this side, that's right. So we'll put x squared on this side, that equals to 1 minus y, and then x equal to square root of 1 minus y. And that only, at this point, we're only considering the positive side of x, okay? And the negative side, it will have to add a negative sign. But for now, we don't worry about that, because the area is equal to then because we are calculating area, we're just going to square something, so we don't have to worry about a negative sign yet. So then what is the, that's just x, which is this distance, okay, which is 1 minus y squared. But we need two of them, so 2x. We need 2x, which is equal to 2 times that thing, 2 times square root of 1 minus y. And then we need to figure out the area, okay? The area of one square, okay, one sample square here. Then the area of the square, I'll write it like this. The area of the square then equals to this thing squared, okay? And which is, if you square that thing, is equal to 4 times 1 minus y. That is our area. And therefore, finally, the volume of all of this stuff is equal to the area, okay? 4 times 1 minus y, times dy, because that's the little thickness, okay? Remember what dy is, okay? And dy, and then we integrate. So that's one of these things, and we integrate. This is 0, of course, and that's 1. So we will integrate from 0 to 1. Yep, and that makes that marks the end of the problem. And then the details of the integration is actually quite straightforward for this problem. Is a simple situation. So then you calculate, you do the evaluation, and then if things are not messed up, then eventually come up with some kind of an answer that's 2. And that is the right answer. With that, let's look at the next problem. Next, let's look at problem 73. The base is the area between y equal to x and y equal to x squared. So that's this thing. That's y equal to x. And down here is y equal to x squared. And then the slices are perpendicular to the x-axis. So a sample slice will look something like that. Okay, perpendicular to x-axis. And the slices are semicircles. So imagine this thing sitting down here, you know, going something like that. And then and we're supposed to calculate the volume generated by such an arrangement. So to do that, then we first have to figure out what is the diameter of the semicircle. The diameter of, so here's x, all right, and the diameter is equal to of the semicircle would be the top value, which is x, minus the bottom value, which is x squared. And that would be the diameter. And then so the area of the semicircle equals to pi r squared, but except that you have to divide by 2, and then the r equals x minus x squared, also divided by 2 to become the radius, and then squared. And that's the area, which is pi r squared. And then x is integrating from 0, okay, to 1, because 1 is where y equal to x and y equal to x squared intersect. They both intersect at 1. And so we then try to do the integration. The entire principle, then we're gonna, the semicircles are standing up here like that, right? And then we'll integrate them from 0 to 1 with dx, because the slices, the dx goes this way. So we're integrating with respect to dx, which means, okay, from 0 to 1, the area and all the stuff, x squared over 2 squared, and then dx. And that, once you calculate that thing, that should be the answer. And yeah, and then so that is again a polynomial, which is fairly easy to integrate, but can be tedious, okay? Which is what I did the integration by hand, as you can see, and eventually I came up with the answer of pi over 8 times 30, which is the correct answer, same as the back of the book. So that must be right. And then, so after that, let's do the next problem. Next, let's look at problem 75, which says you have a bounded area that goes y equal to 2x squared, which is a parabola that looks something like this, your parabola. And then next line, x equal to 0. X equal to 0 is the y-axis. So we're caring about this thing, okay? Remember that. Wait a second. Let me think. Yeah, actually x is equal to 0 is of no concern to us, okay? So next, x equal to 4. So that's the vertical line here. And then finally, y equal to 0. Is this, y equal to 0 is the x-axis, and that's the one that would matter. So this is our region, okay? X equal to 0 is unnecessary information. And then we need to figure out what are we trying to do here. Area of, let me read the problem again. So we are supposed to rotate around the x-axis. Okay, I got it. So here we are trying to do this, okay? We're spinning that thing that way. Now, in order to spin it that way, then we're gonna use the disk method. The disk method then says that we're gonna draw a disk. Here's a disk, okay? That one of the sample disks, and then we need to figure out what is the area of the disk. The area of the disk, the diameter of the disk is 2x squared. Sorry, the radius of the disk is 2x squared. So we'll write that down, 2x squared. We have the area then is pi r squared, where so that's squared. And then the volume then is, then we integrate from 0 to 4 this thing. 0 to 4 and dx. Notice the thickness dx is increasing along the x-axis. Okay, so we're going to integrate along dx, and and that should be it. Yep, that looks about right. And then this integration, of course, is quite simple. Okay, you just have one term, that's x to the power 4th. So the answer comes out very quickly to be some kind of a number called 4096 pi over 5. And that is correct. I checked. And with that, let's look at the next problem. Next problem, let's look at problem 79, where we have y equal to sine of x. We'll draw that thing. Sine of x goes something like that. And then y equal to cosine of x, which comes down. Similar curve, but goes down instead of. And then x equal to 0. X equal to 0 is This one is the y-axis. Okay, it really is this thing. And so then our region is this part right up here, but we are supposed to go around the x-axis still. And therefore we have to, so you imagine this part spinning around, then it will become a washer. That is, we need to figure out what the whole thing is and then subtract it by what's inside. Okay, there are two let's see, yeah, there are two discs that we're doing. So we will follow the washer formula. So let's draw this thing. Okay, that would be the one on top is cosine x, the one on the bottom is sine x, and together that should get us where we want to be. So what is the area? The area for each one would be the area of the big circle. The outside circle would be pi r squared, which is pi cosine x squared. Pi cosine x squared, the whole cosine being squared. And then the area on the inside, which we will subtract, is equal to pi sine x squared. Sometimes we also write it as sine squared x, but I'm not going to do that right now to keep things clear. And then we're integrating from along the dx. See, the delta x is this little width. So we're integrating around dx, but we're integrating where sine x equal to cosine x. When is sine x equal to cosine x? You remember the isosceles right angle triangle, where is 1, 1 square root of 2. Okay, that's when the sine x equal to cosine x. Therefore, when that angle would be pi over 4, okay, 45 degrees. So then we're integrating this whole thing from 0 to pi over 4 of dx. Then area times the little ds becomes a small volume. And then once we perform the integration, then the whole thing will come out. Okay. Yeah, but there's one more point I need to make. That is, if we the cosine squared is not so easy to integrate. I mean, nothing directly becomes cosine squared during the differentiation. However, the fact that you have cosine squared minus sine squared is an advantage here, because there's a trick that you can use. So then what we're going to do is go from 0 to pi over 4. We'll factor the pi out, okay? And then we're going to quote the trigonometric identity, which says that cosine squared minus sine squared is the same as cosine of 2x dx. See that? And once you realize this identity, then things are much easier, because cosine 2x is much easier to integrate, because that's just sine 2x divided by 2. And when you work things out, and then after that, you will come up with some kind of an answer, okay, which is see, over here I have a mess down here, because I forgot that cosine squared and minus sine squared equals cosine 2x. So I was spinning my wheels over here and got nowhere. But eventually I realized, once I realized that, then the answer on this side, okay, is very short. It just equal to pi. You just integrate cosine 2x, and you get the answer to be pi over 2. That's all. All right. Next. For the next problem, we are going to spin around the y-axis. So don't forget that. If you spin around the wrong axis, you'll come up with a completely wrong answer. And so this time, we're going to spin around the y-axis of this graph. So let's quickly see what it looks like. Y equal to 2x cubed. That is the parabola. No, it's not the parabola. It's the cubic. It's the cubic form, but the positive side looks similar to the parabola, and that's all we care about. So y equal to 2x cubed is the line. We're restricted to x equal to 0, which is the y-axis. X equal to 1, which is some 1 here. Okay, 1 line, and y equal to 0, which is the x-axis. Yeah. So what are we spinning? We are spinning this area right here, down here. Okay, don't spin the wrong thing. Anyway, so then this is the area we're spinning, and then therefore our disk has to be done this way. right, going sideways. And as a result, our disk has each of our disk has an individual hole in it. Okay, right here is the hole. So we gotta do the subtraction to take care of the hole. Let's see. Now make sure you pay attention that what you're spinning is this area, not this part, because the x equals 0 is some irrelevant information that might mislead you into thinking that we're doing this part, but we're not. This is irrelevant. Okay, what matters is these three lines, which defines this area, and this time we're spinning around the y-axis. Okay, this way. So remember that. And having said that, that's to spin around the y-axis, things has to be in terms of y. So we'll plug the x out of here to become y. That will be y over 2. Okay, here's x. And then you take the cubic root, or also written down as 1/3. Okay, so then that would be the value of x. And that's x. X is right here. And the whole thing then becomes the large disk, which has a constant area, constant radius 1. So then the large disk is pi 1 squared. Okay, and there's a small disk is this thing, which is pi y over 2/3. Okay, because before it's 1/3, I squared, now it's 2/3. And so that would be the total area that we have, the big disk subtracted by the hole in the middle. When you integrate this thing, then we're integrating from it to dy. And when x is 1, y is, when x is 0, y is 0. But when x is 1, y would become 2. So we need to integrate to 2. And with that, that should be okay. Right. So then once you perform this integration correctly, then you will get the right answer. See, towards the, let's see, the bottom here. And that should be, yeah, the answer is fairly straightforward. And being that we only have, well, I don't know. Anyway, the point is, if you integrate it, you come out with some answer 4 pi over 5. And that should be right. I think that, yeah, that's the right answer according to the back of the book. Next, let's look at problem 85, where we are having, this is a circle, semicircle or something. And when you see a squared minus x squared and the square root, that's a circle. And then y is bounded by some lines. So let's draw this thing and see what it looks like. This is, being that it's a circle, and probably we'll only draw the positive side and see what happens. All right, and then y is 0 is equal to this line right here. Okay, so here's one of the bounds, and x is 0 is this line right here. So we are going to consider this area inside here only. And next is pay attention that we're spinning around the y-axis. Now, being that this is a circle, when you spin around, it's going to create a sphere. Okay, and it really doesn't matter which way you spin it, because y-axis, x-axis, everything is symmetrical and identical. So to calculate the volume of this thing being spun around, what it is remember the volume of the sphere, which is 4/3 pi r cubed. That's something you learned at some point. Okay, therefore the volume then, but when you spin only this part around, you're only going to have a hemisphere, so you're going to be dividing it by 2 here. But otherwise, the radius is 2. Okay, so the volume will be equal to, when you plug radius is 2, then you get 16 over 3 pi, and you don't have to do any integration. Now, but after we have done that, we need to do the integration to make sure that the integration works out. So we are going to do what the book says, which is to spin this thing around the y-axis and see what comes out. To spin it around the y-axis, then we have to plug this thing out, remove, that is, isolate this in terms of x. So x equals to y squared, okay, and then minus Yeah, 4 minus y squared. So by the time you do the calculation, well, I guess I should do it. Good. Okay, let's do this the honest way. So y squared equals to 4 minus x squared, right? And then x squared equals to 4 minus y squared, moving stuff around a little bit. And then x equal to the square root of 4 minus y squared. You notice x and y are symmetrical. You just replace x with y, and then that's because of the circle. Circle is the same way, whichever way you look at it. So then, having said that, then the area, we're spinning around the y-axis. So our disk does this. Okay, this is the radius of our disk. Our disk looks something like that. And then, so the area of our disk is equal to pi r squared, radius being the x, which is square root of 4 minus y squared. And then this thing, pi r squared. And then that's about it. We'll integrate from, this is 2, okay, because there's a 4 there. And that's also 2, so we'll integrate from 0 to 2 of this particular thing, which turns out to be, you take the square root and then square it, so things come out looking pretty peachy. And then eventually, yeah, dy. All right, so by the time you get done all this stuff, then you do come up with 16 over 3, just like the original problem I found, and that's also the right answer. Next, let's look at problem 95, where we have two curves, y equal to square root of x, y equal to x squared. Those are inverse functions of each other, and therefore they are mirror images along the y equal to x line. In other words, they look something like y equals to square root of x, looks like that. Okay, and then y equal to x squared looks like this, and they meet at 1. Okay, this here is 1. And so is that. And then, but we are supposed to spin this thing. So this area is what we're trying to spin, the leaf-shaped thing. And then we are going to spin it around the x-axis. And then, so then we'll draw this thing. So here's a spinning direction. Okay, spin. And then we'll draw some sample line here. And you notice that will be our radius, but the line actually goes all the way down, so there will be a hole in our situation, and which is it's called the washer method, but there's nothing really washer about it. You're just subtracting the big disk from a small disk. So then, so what is this one? Remembering what this thing is. The one on top is square root of x, and the one on the bottom is x squared. Okay, remember that. Which one is which? And then, yeah. So then our area then equals to the big sphere. We're spinning this way. And then, so the big one is pi equals to the big one, pi square root of x squared, minus the small one, which is, again, pi x squared squared. That will be the area. So then the volume then, actually, let me erase this statement here. So that's our area, and then our volume is then integrating along the x-axis. Okay, here's our little delta x there, which represents the x. So we will integrate this thing, dx, from 0 to 1. Okay, because yeah, that's where they intersect. So we'll integrate from 0 to 1, and that should be it. And so this is again a simple integration, because the square root got squared to just x. That's x to the power of 5. And when you get it all through, then you get the answer, which is pi times 3 over 10. And that is the right answer. I checked. So next, let's look at the next problem. Next, let's look at problem 101, where you have a bunch of stuff. X equal to e to the 2y, x equal to y squared, and then y equal to 0, and then y equal to natural log of 2. Now, what does that look like? So I plotted it into the Desmos calculator, and it shows me very nicely something like you can just type it in like this without changing any variables. Type in x equal to e to the power 2y, and there comes well, what does that look like? Okay, y equal to, okay, so y equal to 0 and y equal to negative. So it looks something like this. I will copy that down here. That's the x-axis, and then yeah, and there's a line here. That's y equal to natural log of 2. All right, so far so good. And one of the lines look like this. Ugh. This is the parabola. Yes, this is x equal to y squared. Okay, that refers to this line here. And the other line looks something like it goes from this point over here, goes all the way down to 1. Okay, so the other line looks like this. That is the e to the power 2y. All right, so there's that. And we're supposed to spin around the y-axis. Therefore, that's the y. So your disk looks something like that. Okay, let's draw one of the disks. And as you notice, the radius of the disk has to be subtracted by the hole again. So and therefore the equation, as always, is equal to the big one, okay, which is pi times e to the 2y, that's squared. That's the big circle, and then big area minus the whole. The whole is the small area, which is pi times y squared squared. That's the small radius. And once you've done the subtraction, then that's the area of the washer, and then you take derivative of dy because we're spinning around the y-axis. Very important. Okay, we're spinning this way, so this circle increments this way. Okay, so delta x is this little slice in the y direction, and we'll sum this thing up from 0 to natural log of 2. And that's your that's again a fairly simple integration to do. And then and that's what I did, and eventually equals to some fairly complicated answer that I'm going to show you. Okay, here let's see. Yeah, that is the problem. All right, so that's the answer. Is when you get through all that, you come up with an answer that's fairly long but straightforward. And that's that. And next, let's look at the bundt cake. The bundt cake is generated by y equals the sine of x, okay, which here's sine of x going from 0 to pi. Here's pi. And you spin this thing around the x-axis, then you get your bundt cake, as is shown in a picture in your book. Now, to calculate the area of the bundt cake with a disk, we're using the disk method, is actually not that simple. So for this problem, you're only required to set up the problem without finding the answer, because the integration involves the integral of sine inverse of which we haven't covered it yet. So so you only have to get the problem set up right, and that should be good enough. Now to set up the problem, now you have one graph, okay, but the problem is then you have, all right, I guess this part doesn't matter so much, but we have to integrate along, spin around the y-axis. Here's the spinning circle. Okay, spinning around the y-axis, which means we have to use the sine function and then subtract it by the sine function again. And how are we going to do that? Well, we're going to do that by paying careful attention to the inverse of sine. So being that we're spinning around the y-axis, that we have to do dy, okay? And then therefore we will extract x. So x equals to sine inverse of y. All right, and at that point we have to be very careful about the definition of what that means. And now notice that the sine inverse is only defined here. In other words, if you plug in what is the sine inverse of y, that you're only going to get this part. You're not going to get this whole thing. So how do you get this whole thing? Then the first radius is you can the whole thing is the same as pi, which is the entire distance, minus the little part, which is the sine inverse. Okay, each of this little part is the sine inverse. So then the radius of the big disk is pi minus sine of inverse of y. This is because the definition of the inverse function. So that is the big radius. Okay, you take the whole pi minus the small part. These are the one of the small parts, and you are left with the rest. And then that's the first radius, which we will multiply it by pi r squared, right? I mean, make it pi r squared, and then minus the whole. The whole is just the sine inverse, the little thing. So then minus pi sine inverse y squared, and then so that's our area. Okay, and then so the total the volume of the disk, I mean the total spinning solid, then goes from 0 to 1. Okay, the point up top is 1, 0 and 1 of dy. And once you figure that out, then that should be that will be the answer to the problem. Now, if you clean this expression up a little bit, multiply stuff out and things, then you do find yourself in a somewhat decent position where some of the square can't get subtracted out. So then you end up with something like this: pi times pi squared minus 2 pi sine inverse of y dy. And we're still having the problem that we haven't covered the sine inverse yet. So that's all the more I expect you to come up with. There is a formula that you can go after, or you can use the definite integral calculator to eventually come up with the answer, which is 2 pi. Right, but that part is not as important because we're not quite ready for it. But what matters is that you figure out how to set up the problem. That's the most important part. Now let's look at the next problem, which I think is also the last one. Actually, before we move on, I suppose I should show you what I did. See, the sine inverse is actually just the pi minus the other part. If you look at the graph, then you realize why this is the case. But again, we haven't covered it yet, so I don't know that you need to figure that out right now. So let's just move ahead to the next problem. Next, let's look at problem 111, which says you have two circles and they are actually two spheres. They intersect in such a way that the distance between the middle of the intersection to the center of the spheres is h. Okay, so the total distance between their centers is 2h. Now the question is, what is the volume of this intersection, a football-shaped object? Well, right now it's football-shaped. If the thing comes closer and closer, then you look rounder and rounder, look more like a sphere. Or if it gets far pulled apart, then it just gets very small, right? So then we need to figure out the volume of this thing. Now to calculate the volume of this thing, let's draw a different graph where we only see the circle, see one of the circles, and then here is what we're spinning, right? We're spinning the circle, which is square root the area, the radius, the formula of the circle is equal to this, square root of r squared minus x squared. And then that would be this is r, and that is just r squared minus x squared. And then we're going to spin this part. We only need this part, okay? And then we'll double it because this has two of them, right? There's a top part and bottom part. So we calculate one half of it, and then we double it, and that should come out. And what is that? That this is this distance is h, okay? And the whole thing will be r, being that it's a circle. So knowing that we have, and the height here is r squared minus x squared. Now our disk, our spinning disk, then our sliced disk will look something like this. Okay, now I'm drawing it in perspective. So you imagine the disk spinning around like that. So what is the disk? The area of our disk will be pi times square root of r squared minus x squared squared. That would be the area, okay, of one of the disks. And then all right, so that's about it. We don't have a hole or anything, so we don't have to subtract anything. And so we're going to integrate. We'll integrate the disk will go from h all the way to r of dx, right? Because the thing will spin this way. We'll spin this area down in order to create that. All right, so far so good. But don't forget, we need two of them. Okay, if you forget the two, your answer is only half as big as it should be. And now that we have done that, yeah, that's about it. And then the answer that I got is equal to 2 pi times a bunch of stuff, which is 2r cubed divided by 3 minus r squared h plus h cubed divided by 3. And that is the right answer. Now, the book gives a completely different answer that I know is wrong because how can I tell that that I didn't mess up? That it isn't me that messed up. Maybe the book is right. The reason I know this is right, and let me show you what I did so that you can see it. The reason I know it is right is because when you look at the volume, this is what I claim the volume to be. When you look at the volume, if you let h go to 0, right? And so the h is shrinking, in other words, the two spheres are coming together to become one, then h goes to 0, then the whole volume becomes 4/3 pi r cubed, right? That is the volume of a sphere. So that's right. And then if you let h go to r, so that h goes all the way down so that the two spheres only touching each other, if h goes to r, then there won't be any volume, right? If h gets to be as big as r, this area goes to 0. So if you check this point, as h goes to r, then this does go to 0, because if you imagine h to be r, then there's 2r cubed plus 1/3, that's 3/3 minus it is 0. So these checkpoints, though it doesn't conclusively prove that my answer is right, shows that it's likely in the right direction, whereas the answer of the book doesn't satisfy any of these conditions that I checked. And that's why I maintain that my answer is correct and the answer in the back is wrong, because when you let r equal to let h goes to 0 or h goes to r, the answer of the back doesn't go to 0 or the volume of the sphere or nothing. Okay, it just goes to some random number. So with that, then we conclude this section.